Hi and welcome back. This is the last little bit that we're going to look at in terms of HL bonding, and this is just a recap of delocalization and talking about hybridization and how it affects it. So we've looked at delocalized electrons, and we tend to see these in resonance structures, or in particular in our structure of benzene. So we know that pi bonds form from the electrons in unhybridized orbitals, that sideways overlap. Okay, so that pi bond, that second bond in the C double bond C, is caused by that sideways overlap. When we have these, we have two situations that we can see. In something like ethene, the pi electrons can't change position, so they're said to be localized. We have the one double bond. But when we get conjugated pi systems, which is alternating single and double bonds, the pi bonds can change position. These pi electrons, these p orbitals that we have here forming our pi bonds, what we end up getting is this region where the electrons are free to move, so they delocalize. Okay, they can change position through the pi bonds because of that sideways overlap, and we get delocalization of the pi cloud or the pi system. The distribution of electrons within a pi bond can be referred to as resonance, which we've heard before. Okay, this is different to resonance structures, though it does have some similarities. From this, we know, of course, with benzene, this idea of resonance and the delocalization of the pi cloud means that we have physical evidence for the way that this occurs, i.e. if we didn't have this delocalized pi cloud, we would see alternating bond lengths between with a single bond and then a shorter double bond, but what we see is a constant bond length, which is about a 1.5 bond order, so that between a 1 and a 2, but no clear 1 and 2 alternating. We see a similar thing with ozone, where we have the 1.5 due to the 3 oxygen atoms being in that resonance hybrid. So with benzene, the C-CH bond angle is 120, and this is a trigonal planar shape around each carbon, of course, because of the 3 negative charge centers. This means that the carbons in benzene are sp2 hybridized. The third p orbital of each carbon is perpendicular to the ring, so this causes our delocalized cloud above and below. So each leftover p orbital overlaps to form one delocalized pi bond right around the ring, with the unpaired electrons within this pi bond. So that fourth electron is now delocalized within this ring. We can see this also with nitrate anions. Again, the oxygen-nitrogen-oxygen bond is 120 degrees, indicating a trigonal planar geometry, molecular geometry around the nitrogen. As with carbon, nitrogen will have hybridized orbitals when it forms these bonds. So you're going to have 3 negative charge centers, so the nitrogen will be sp2 hybridized, okay, and then you're going to have the same for the oxygen. The third p orbital for both of each atom is perpendicular again to the plane, giving us sideways overlap throughout those p orbitals. So this p orbital overlaps to form the delocalized pi bond across the molecule. Okay, so we have that resonance hybrid for the nitrate anion. You can go to your text and see other ones. There's the carbonate anion, there's the ethanoate anion. But essentially this is taking us back to the idea of our resonance structures, and we get the idea of resonance structures where we can draw resonance structures gives us the information that there is delocalization within that molecule, okay? And we know that delocalization can occur when we have different Lewis structures that all fit the bonding rules, and there is evidence of the bond length and bond strength giving us an intermediate length between a single and a double bond, or an intermediate strength between a single and a double bond. So we don't have pure sigma pi single double bond. We have a delocalized electron making all of the bonds equal. Okay, that's it for HL bonding. Now we've just got to put this into context and practice with some exam questions, and I'll see you in class.